All right, let's try number 9 here. Number 9. So we have a piecewise function. It says let f be the function defined above. For what value of x is f continuous at x equals 2? And you see this a lot when you study continuity. A discontinuity would occur when there's a place informally that you would have to pick up your pencil to continue drawing the function. So what we want here is for these two functions to agree at the value x equals 2. Both of these functions, this rational function and this constant function, are both going to be continuous for all of their domains. Well, except at x equals 2. Okay, you can't divide by 0. And that's why there's a break here anyway. But otherwise, these will always be continuous. So the only possible place we could be discontinuous would be if we don't have the same y value when x is 2. So what we want to do here, let me write this down. 2x plus 1 over x minus 2. Okay. Let's go to the board here. All right, so when x is 2, we want those to be equal. Now, if I put it 2 in there right now, it's just going to have a 0 on the bottom, which is what we call a hole in the graph when you're studying rational functions. But it's nice and factored already for you, so go ahead and cross that out. So we have this, and remember our x value in question is x value 2. So I'm just going to put a 2 where x is. Okay, so that makes k be 5. All right, so for what value of k? It would be 5. K equals 5. It would be correct for number 9. So that's E. All right, number 10. It says, what is the area of the region in the first quadrant bounded by the graph of y equals E to the x over 2 power and the line x equals 2, okay? Erase this one. So, of course, area, you think of an integral. Write it down here. And it always helps. My advice to you would be to know these graph shapes. Just kind of have an idea of these graph shapes for a question like this. Okay, you know e to the x is an exponential function. E to, when I start tinkering around with that exponent, it will change the steepness of the graph, but not really the shape. So it's going to look something like this. It's going to be a basic exponential function. And then you're going to have a vertical line here at x equals 2. That's going to go through here. So we're looking at this region right here. All right, so we want to find the area of that region. So we're going to take the integral, and the x values here are clear, between 0 and 2. Let me go back and make sure it said that. In the first quadrant, right? So we don't venture off. That would be something called an improper integral, which is later if you were to venture off in that direction. But we go from 0 to 2 here of e to the x over 2 dx. Now, clearly, a u sub would be in order here. Okay, so I'm going to let u be 1/2 x, which is naturally, think of the chain function, the function inside the function. Okay, so the inside function is what you want your u to be, and your derivative of u with respect to x would be 1/2. Okay, therefore du is 1/2 dx. Right? So we can take this then, this integral. I'm going to write it down here. I'm just going to erase this, just have some room. So I'm going to write it as e now to the u power dx. Okay, but since I'm changing things over to u, I need to change my limits here. Okay, because we're going to be, we got to fix this dx also. Let's go ahead and fix these limits. by just putting them in here. So if I put this x limit into this, u equals 1/2 times 0. That's still 0. But if I put this x value 2 into this, 1/2 times 2, it makes u value 1. Okay, so I'm going to change that to a 1. And we can't have a u and an x there, so let's fix this. We need this to be 1/2. We need a 1/2 in there. So I'm going to put a 1/2. And to compensate, we're going to put a 2 right here, which is perfectly fine. So this becomes 2 times the definite integral of e to u. And now we have du. This is du right here. Okay, so now I'm ready to go. The antiderivative of e to the u is e to the u. And I have a 2 here. I want to evaluate that between 1 and 0. Okay. So I put the 1 in there. It's just 2e. If I put the 0 in there, it's 2 times e to the 0. And remember, e to the 0 is 1. Okay, so we have 2e minus 2. Or they may factor that 2 out. I don't know if they will or not. We'll look at the answer. Yeah, so it's like A. 2e minus 2. So 10 would be A in this one. All right, so let's check out 11. So we have time to do 11 here and what this is. All right, so it says let f be the function defined. Which of the following statements is true? So again, this is one, we have one similar to this earlier, which said which one's false. So here, which one's true? All right. So, and this is a function using calculus terms. It's an absolute value function. So I'll write it down here. And inside that absolute value function is actually inside of a square root function. So it wants to know specifically what happens at 2 for this graph. What happens there at 2? So is it continuous but not differentiable? Is it differentiable? Of course, if it's differentiable, it has to be continuous. Is it not continuous at all? Does the limit not equal 0? Or is x equal to a vertical asymptote there? Okay, so those are things that we need to consider. Again, it helps to think about the graph. So let's look over here and see if we can think about the graph of this. What I'm first going to do is just graph x minus 2, which you should cover in pre-algebra, the square root of x minus 2. So forget the absolute value bars for just a minute. The square root of x minus 2 would actually be over here. Right? And now we're doing the absolute value of that as well. And what that allows is ordinarily the square root graph just abruptly stops here. Okay. But because we're doing the absolute value, we can actually put some of these values into it. Okay. Values such as 1, which beforehand, without the absolute value bars, it just wouldn't show up on the graph because 1 minus 2 is negative 1. The square root of negative 1 is imaginary, which won't show. But if I put 1 in here now, 1 minus 2 is negative 1. The absolute value of negative 1 is 1. And I can take the square root of that. It's actually going to be 1 here. Similarly, if I put a 0 in here, I get the square root of 2. And what it's going to do is make a graph that looks like this. Okay. Now, how do I know that? Well, it's because there's no pre-algebra. And you just have to know the nature of graphs and what absolute value does. Okay, I wish I had a better, cleaner answer than that. That's what it is. And we can now look at the graph and ascertain all we need here. It's definitely continuous, okay, but it's not differentiable because of this sharp corner. All right, the limit is 0 here. Remember, limit's at y value. So when x is 2, your y value is 0. So limit's good. There is no vertical asymptote. That's not a vertical asymptote. Okay, so the answer would be it is not differentiable. Okay, let's look back at the problem. So which of the following statements is true? It's going to be A. You are continuous, but you're not differentiable. Okay, we'll stop there for this one.